So if you remember from the last video, this is what we had, okay, for X components. We also have this same thing for Y components. We also have the same thing for Z components. But bear in mind that whatever we do to this, the X, the one there in X, okay, X, whatever we do to this is the same thing we'll have when we do for the same thing when we have Y. The rest is being the same, okay, also for Z. So instead of doing something to all three of them, we just do to one, and the final result apply it to the remaining two. What are we actually doing to them? In fact, where are we heading to? Where are we heading to? Now this is it. This guy, remember this is what? Magnetic vector potential, right? Magnetic vector potential. Okay, the same thing here. Then this guy is the source current. Okay, source current. Source current. Okay, yeah, source current. Pardon the writing. Yeah. Now, the thing is we want to know electric and magnetic field. This is where we are heading to. What is the electric and magnetic field produced by an antenna? Okay, if you have an antenna here, what is the electric and magnetic field that will be produced by this antenna? For you to know the electric and magnetic field, you have to know the magnetic vector potential. Okay, for simplicity, the magnetic vector potential. But to know the magnetic vector potential, you have to know for each component, the X component, or let's say the Y component or the Z component. Okay? And for you to even know any of the components, you need to what? Know the source current. You know the source current. Okay? Maybe for X or Y or Z or the general source current, which is what we have here. Okay, now all this process has all been derived before now, years back. We are just learning what has been simplified already, even if it doesn't appear simplified right now. It's actually simplified if you think of what those in those days went through in simplifying this. Okay, so this is where we're heading to know the electric and magnetic field, right? We have to know the magnetic vector potential. This pattern has been derived years ago. We are just learning it. All right. So the source now point. If we know the source current, this is where we start now. If we know the source current, remember this is what equation 15a, right? But let's just call it equation I. Kind of the way it was done in class to simplify it further. So call this equation I. So now we just took out of, let's see this, 15, 15a, 15b, 15c. So we just took one of them. Instead of, if we have the source current, what will happen to this equation? If we know source current, the next thing is to what? Is to know this, this, and then know this. What am I doing? Know this. Then we can know this, and then we can know this. Clear? So if we know this, we'll now address this, and this. But instead of addressing this, let's just address only one. I think I've said that in this video. Let's address only one. Once you address one, your final answer from addressing one, just apply it to the rest. And then we can now face this one. So, in a situation where we know the source current,
and that will be
if
in
we
the next
know the source
video.
current, what is the formula? Or how do we go about it? A guy named what? Green. Okay, he has a function that addresses this equation. That's the one for magnetic vector potential. The Helmholtz equation. Look at it here. This 15a, b, and c, they are what? Scalar inhomogeneous because there's a source. Inhomogeneous, so it tells you that there is a source. This thing is equal to something. If this thing is equal to 0, it's homogeneous. but it is not equal to 0. So it's what? Inhomogeneous. Equal to 0, not equal to 0 simply means this expression is produced or caused by something. There is a source, which is this, a source current. If it's equal to 0, that means there's no source. That is, it is homogeneous. But this our guy is what? Equal to something. There's a source. So it's what? Inhomogeneous. So these are scalar inhomogeneous Helmholtz equations for the component of the magnetic vector potential. Components of magnetic vector potential. X component, Y component, okay. X component, Y component, Z component. All are for the what? Magnetic vector potential. And the JS is the what? Source current. So, yeah, these are scalar inhomogeneous Helmholtz. What did I say? Helmholtz equations for the component of the magnetic vector potential. We can obtain an integral form of the solution to each equation starting with this one. Just pick one of them and they call it this. Like what I said, pick one. So let's address that one. So if we know the source current, this guy, Green, gave us a function to address this expression if we know the source current. And what is that? What is that? He said that beta naught square, okay, plus what? Nabla square multiplied by what? The Green's function. The Green's what? Function will be equal to what? Negative small change. Then you now have what? The Green's. You have this. Okay? There. Yeah, that's correct. But I think I switched the order. Yep. So that's it. So what does this and this mean? We're going to tell you what that means right now. Please, arrow bar, this. Let me draw this thing so that you just imagine you have this as an antenna. Okay, you have an antenna here. And then this is where we are, right? This is where we are. Sorry, this is where the antenna is. Then if you are observing the antenna from a particular distance, or what will be the effect of the antenna on at this particular distance away from the antenna? What do we observe from this point? Look at this distance away from the antenna. So at this point is what? Arrow bar. At this point is what? Arrow bar prime. So this is the arrow bar prime, the source where we are getting that electromagnetic wave from. Okay, then this is what? Where we are observing it from. At this point, at this location, what is the effect or what do we get from the antenna? So green, then G for green is a function of what? The observation point and the what? The source point. Of course, equal to negative small change in what? Small change being the function delta, okay, delta being the function of what? The observation point and also a function of what? The source point of the antenna. Now, look at this expression we have here. Let's call this equation 2. Sorry, this will be equation I. I don't have other space here, that's why I'm doing that like this. Okay, is equal to phase change during what? Propagation, right? All over what? Spreading distance. And this thing, we have it in our notes as this. So this is the phase change. You can see beta naught there. Phase change. All this thing on top here equal to that thing. Okay? All equal to that thing. Then the spreading distance is equal to this. But this arrow we have here, that arrow equals what? Equals this. Which is what? The equals modulus of what? But this r equals what? The modulus of what? R bar minus R bar prime, meaning a point in the source, like I drew that antenna some minutes ago, a point in the source, and we are going to subtract that value from where? The point of observation. Of course, take the modulus, meaning whether positive or negative, you get a positive result. That is what R means in this case. All right. So that's equation 3. Okay. Equation 3 and what's equation 4? Now, what we are going to do, this is where we have the important parts of simplification. And we'll do that in the next video.